The next presentation, the first presentation, will be given by Niels, who is a partner at Dynaflow Research Group, and he's one of our main experts on our in-house developed software code, BOSfluids, which will be the subject of his presentation.
Okay, thank you all. I'd like to give you a presentation. There's a little less time than foreseen, but that shouldn't be a problem. I will try to run into the schedule so that the following speakers will not be shortened on their presentation. My presentation will be about basically about BOSfluids. It's our in-house developed software. It's been commercially available for about 10 years now, and I will show. We will have some new developments on it, and I will illustrate some of it, some of its uses. It's using one of the cases that we've done for a consulting project, which is a Nafta loading line. So to kick off with BOSfluids, maybe people in the room have heard of it. It's a 1D single phase flow solver. It uses it's particularly suited for pipe systems, since pipe systems can be assumed to be 1D. It is single phase, but there are some elements within the software that can handle some more complicated multi-phase elements, such as a search vessel, for example. It uses the well-known method of characteristics to solve the flow and the pressure within the system. I assume most of you are familiar with the method of characteristics. It's been very old, been around for quite a while, and well known and well tested by us, but also by many others. It's typically valid for relatively small time scales, as in the order of minutes, and it, especially ours, doesn't solve for temperature, so temperature is supposed to be stable. The software is ideally suited for different type of analysis. So for example, on the left hand side you see for the steady state, you can use it for pipe sizing, pressure loss analysis, and pump specifications, which is often used at the start of a project, but you could also use it for transient analysis, and at the bottom you see some of the type of analysis that you can use it for. Typical applications: sewage systems, oil production lines, tanking, loading, unloading. That's one of the things we will treat in the case. LNG systems, cooling waters, and different dynamic behaviors. It has been around for about 10 years, and relatively recently, over the past few years, we have improved the engine significantly. We speeded it up, took some errors out of it, and also added more of the vacuum capabilities for large cavities. And then this year we will also release a new version, version 5.0, with a new interface. We're coming from the left-hand side, which, so as you can see, it needed some upgrading. And this is an example of the new interface. I will show you some of the features that are included in the new interface. The interface will be released in a month from now. So this is how it will look like. On the right hand side, which is it has a very detailed model, 3D model of the system at hand, and on the left hand side you see the input data. And there's a real-time interaction between the two. So if you select in your system one of the pipes, like for example the yellow one here, it automatically tells you the data related to that. Most of the method of characteristic systems around are more 2D, have a more of a 2D network type of interface. This is particularly well suited for continuous analysis, for example, dynamic load analysis, in stress type analysis, dynamic analysis of the piping system itself. As you see here on the left, you start off with the model, piping, boundary conditions, and analysis parameters. You continue with scenarios. You can enter different scenarios, and then there's a running tab, and then you will be able to post-process the information using the results tab. There are many improvements. Well, the user experience has become much easier. It will more guide you more easily through the software, making it easier for the user not to forget things. And there's also a lot of error checking going on the fly to make sure that you're able to run a good analysis. The 3D interface allows you to have a continuous evaluation of the system you're building and whether everything's still in line with what it's supposed to be. As I said, there's clear node numbering and interaction between the input data and the system itself. It allows now for group modification, so you can select different elements at the same time and modify as groups. You can also bundle elements with different, say, flow parameters or different pipe parameters and post and pre-process them simultaneously as a group at the same time. It has the scenario builder. Before you had to save basically every scenario in a different file, and now everything's done at the same time. So you can stay within your data, within your single file, and create different types of scenarios. There's an import-export feature, which is very interesting for many people that continue with the analysis. So, for example, the unbalanced loads that you find from your analysis can be used in the dynamic pipe stress analysis, and this model allows you to use the same model and insert it in a pipe stress program and vice versa. And there's a lot of improved post-processing, which is very handy for interpreting the results. Most often with this type of software, it's relatively easy to make the input, but some of the phenomena that you see can be difficult to interpret, and therefore good processing availability of, say, 3D and 2D graphs make it easier to understand what's going on in your system. And there's also some software interaction that's been improved. So I will show you if it works. An example of the 3D interface post-processing. So what you see here is that this is just an example system. It has a valve here, a boundary condition, and the valve will be closed. And what you see is then the result in this 3D feature, while here at the same time you see a 2D plot. This is the distance axis along this line, and here you see the pressure varying over time. Let's see if we can make it work. No? So you see the pressure wave bouncing back and forth within the system, both 3D and here on the bottom on 2D. Resolution is so-so, but on your own laptop it will be much better. So this is something which, I mean, I don't know how many of you have experience with interpreting this type of results. I assume quite a few. It's really handy so that you can see whether there are no anomalies in your system, and that the results make sense from different type of aspects. Okay. An example of a case that we've done, a project that we've done using BOSfluids, using the old interface pattern. This is it concerns a Nafta loading system. It's a 600 millimeter diameter pipeline loading Nafta from a ship to a tank. There's a loading arm involved, and the Nafta has a vapor point of minus 0.2 bar, which is relatively low, well, high, so to say. So it's something to watch. The transit scenarios the client was interested in was the closure of the tank valve and the closure of the ERC valve, which is near the loading arm, and the pump trip. In this particular case, because the pump, it was an offloading system, so the pump would be at the ship, and therefore it was a sort of an unknown variable. We didn't have much information about the pump because it depended on the ship that was going to be there. So we tested some various, two different types of pump trip, pump with very low inertia and one with a little higher moment of This is how the system looks like. You can see it here in the bottom, on the bottom. So this is the loading arm. This is the detail of the system. There's a few valves here, and there's the ERC valve, which we will open and close. This is the tank section. There's a siphon type line here, and this is the valve that will be operated. This is the old loading section of two different jetty, which is just there, but is not being included in the dynamic scenarios. The three scenarios that we will check is the closure of the tank valve, the rapid closure of the ERC valve at the loading arm, both different variations, and the pump trip also with two different variations. So the first scenario, the tank valve will close in about 20 seconds. So this is the results we found in 2D. Here you see time and pressure, and you see two different types of closing of the valve bubble. As you would expect, the more softer closure of the valve, where you decrease the closure rate, will have a nice effect on the pressures. So it will produce less high pressures and less fluctuations. You see it here on the upstream side of the tank valve, particularly on the downstream side, which is a much shorter line, and also there's back pressure from the tank. Then, if you can continue, you will see that the pressure oscillates. The pressure oscillations propagate through the system, and there was particular concern, and we'll flip back in a minute, on about these road bridges. There are quite a few in them in the system, and each of them had to be supported, and there was a lot of concern whether they would see high loads and might not be strong enough. So what you see from these pressure variations at the fourth bridge, which is the one furthest away, it's also that the loads are quite high, the unbalanced loads resulting from this pressure. The second scenario is the rapid closure of the valve at the arm, and there it was kind of interesting because at first not much happened, but then when the system came to a rest, it seemed, then at some point later in the simulation we find this enormous spike. At first we were a little bit surprised, of course, to see this spike, and we were thinking about maybe a numerical. If you run this type of numerical software for a very long time, then at some point it starts numerically sort of deviating. So at first we figured that it might be something like that, but then we looked more closely and we found that that's absolutely not the case, and it had to do with bubble collapse. Because what would happen at this relatively high points at the bridges and at the siphon, the vapor pressure would be reached for the Nafta. So the high points would be completely vaporized, and then when the system seemed to be more or less coming to a rest, then the pressure would go up again, because of either the back pressure or the continuous operation of the pump, and the bubbles would collapse, causing these enormous high spikes. And of course, these spikes propagate here, and they would cause extremely high unbalanced forces, which I don't have a graph of here later on as well. So this here, it created unbalanced forces in the region of about 300 kilonewton, which were extremely high, and of course the road bridges were unable to accommodate those high pressures. We continue with the pump trip, the unexpected pump trip. As I said, we did two variations. One is a 5-second shutdown and a more instant shutdown with a very low moment of inertia, where the pump would shut down in 0.1 second, which causes a little bit more extreme pressure spikes, as you can see here. But basically, the main phenomena here, the bubble collapse, for that it didn't matter so much how fast the pump would trip or how fast you would close your ERC valve. We do see both phenomena. Okay, and again, these propagate through the system. And there you see, this is a picture of the unbalanced load after the 5-second shutdown. So you see that they're extremely high, and in this scenario also not 280, but still quite high, around 100 kilonewton. So the first was to check whether this road bridge could actually handle this type of loads. And from the dynamic analysis, it was quickly found that it was impossible to do so. This is, by the way, a picture from Caesar 2, which is a pipe stress program where you can see the steel structure included in the dynamic pipe analysis. So the conclusion was that these high unbalanced loads could not be withstand by the axial stops, even if they were strengthened, and especially on the top of these bridges, it was very complicated to create axial stops that were able to withstand that type of force. So we were thinking about, we were trying to come up with different other solutions to reduce these pressure spikes. So we checked things like surge vessels, air valves, different type of closure, different back pressure by the tank, etc. And one of the things that we also tried, and actually worked best, although I'm going ahead a little bit in the presentation, is the coupled operation of valve. That's actually also the easiest way, the easiest method to implement, because it has obviously very low capital cost. The idea is that you would operate several valves at the same time, and try to isolate or make compartments of the different pipes, of the pipe into pipe sections, and therewith making the flow come to rest more easily, and therewith preventing the bubble collapse, which was causing these high pressures. So we show you some of the results that we achieved. So the first one is the lid closure of the both valves. So this is the EPC valve scenario, where the valve at the loading arm will be closed, and simultaneously, while it will be closing, we also close the valve near the tank. This is the scenario 2. And what you see here is the green line. The red line was the original simulation, and with it coupled, you see that this enormous pressure spike is much smaller. The same you'll see upstream of the tank valve. So between the tank valve and the tank, also the pressures are much lower, and you can see that it comes to rest much easier. The most important thing, of course, is how do the unbalanced loads develop. And here we see quite an extreme difference between the two ways to operate the system. This enormous high unbalanced loads has completely disappeared if we couple the two valves. Then, of course, it would be interesting to see how it would operate in the scenario where we not close the EPC valve, but where you would do the pump trip. And basically, so once the pump starts tripping, you start also closing the tank valve. This we simulated here as well, and basically you see more or less the same behavior, the complete disappearance of the bubble collapse. So, what are the conclusions from this particular case? Is that the pressure oscillations propagate rapidly and result in high unbalanced forces. The road bridges had problems with these unbalanced forces and could not withstand them, so different types of solutions had to be found, and that the coupled operation of these valves could diminish the unbalanced load significantly, and therewith make it an easy way without many capital costs to make it a safe system to operate. And it also shows, and I think that's a bit of my concluding remark, it shows that with using BOSfluids you can well capture vacuum and bubble collapse over systems like this. And although it doesn't have temperature in it, some of the phenomena, such as vaporization, are well captured within the software. That's the end of my presentation. Please, any questions?